Thank you very much, Fateh and Beatrice.
Thank you.
And,
Thank you very much.
Thank you. So we will go to the next, to the first session, session 1, about dynamic safety anomaly assessment. So I will invite the first speaker, Huang, to present feature space singularity for out of distribution detection. Huang, are you there?
Oh, yes.
Great.
Hi.
If you can share your screen, or if you want, I can share your presentation as well, as you want.
Okay.
Okay, we can see your screen very well.
Great. So, okay. So, good morning, everyone. I'm Huang from University of Oxford. In this talk, I will introduce our new paper, which presented a new observation of neural networks. And this observation leads to a simple and effective out-of-distribution detection algorithm, which can contribute to trustworthy and safe AI systems. So this is a collaboration work with my colleagues at both Peking University and McDermid Technology. So first, let's look at the background. AI safety, or AI trustworthy AI, is a huge topic. So what we discuss here is that current AI systems do very poorly with OOD data, out-of-distribution data. And indeed, their predictions can be arbitrary on data from unseen distributions. This is very common in the real world. So for example, an autonomous system, autonomous driving system can produce confident but terribly wrong predictions on unseen traffic signs. And this can be really dangerous. So what we want to do is to detect these OOD samples, or equivalently, assign higher uncertainty estimates on these data. And then we may integrate manual intervention on detected OOD samples. So there are two major concerns in OOD detection research: performance and computational cost. So currently, the best performance is achieved by ensembling multiple independently trained neural networks. So, but this is computationally expensive. So our question is, can we use a single model and still achieve high performance? So here is our observation. We discovered that out-of-distribution samples concentrate in the feature space. So here is an illustration. We use MS1M dataset as the training data to train a ResNet model. So MS1M is a face recognition dataset, so it contains millions of human faces. After we train the model, we extract features of the last layer of MS1M and ImageNet data, and then we do PCA. So this produces the right plot. As we can see, that out-of-distribution data, here the ImageNet data, they lie in the center, while MS1M data, they lie outside. And if you can imagine the real high-dimensional feature space, the concentration is actually much greater. And besides ImageNet, we find that, in fact, all kinds of out-of-distribution features concentrate in the feature space. So to make it a general method, we approximate the center of the OOD by using the mean feature of the uniform noise input. And we call it feature space singularity, which is the black dot here. We then calculate the ideal distance to this point, FSS point, in the feature space. Then we have we call it the distance to FSS, or FSSD, and we have the left plot. We can see that the smaller the FSSD, the more OOD the image is. And here, the more different from the human face the image is. We find this concentration phenomenon kind of universal. We tested it on many different conditions, and we found that they all kind of have the out-of-distribution concentration phenomenon. So why is that? Here is our explanation. The reason is different data have different moving speed in the feature space during training. Here we can analytically calculate the moving speed of the speeds, which is the DFDT. And we can see that the moving speed is actually essentially measured by this quantity, the inner product of the gradients between the test data, X, and the training data, XM. So this acts like a similarity function between test data and the training data. And this term is actually the neurotangent kernel, the empirical neurotangent kernel. And when X is out of distribution data, this quantity tends to have smaller values. So here we visualize both the features and the moving speed at different training time steps. So we can see that indeed the OOD features, here are the orange features, have smaller moving speed. And over time, you can see that they have smaller movement in the feature space, which is just the FSSD. Now we can look at the algorithm experiments based on this phenomenon. So we designed this algorithm based on FSSD. But instead of using only the last layer, we can actually ensemble all the layers in the model. This can be done by a single forward pass to collect the features. So the computational cost only increases very slightly. And we also have a perturbation step here. This is actually a common trick of the OOD detector to enhance the performance. So you can find the intuition and some analysis of the perturbation step in this paper. So I will not cover it here. For out-of-distribution detection task, like the previous MS1M and ImageNet example, we will have two test datasets, one in distribution and one out of distribution. And the OOD detection algorithm will assign scores to these data to separate them. And we will use these three metrics to evaluate how the algorithm is doing. So here are some results of our experiments. We implemented 7 different out-of-distribution detection algorithms, and we compare them on various data sets with different scales and different data types. We can see that the FSSD algorithm performs consistently better than other methods. Besides completely different out-of-distribution data sets, we also conduct experiments to detect corrupted data sets. So these corrupted data sets are constructed by adding some manipulations to the original data, like Gaussian noise, shot noise, etc. And we have 16 types of corruption, and each corruption has 5 different levels. So together we have 80 data sets. For each of them, we conduct experiments to distinguish the corrupted data set and from the original uncorrupted data set. So for each method, we have 80 experiments, and we have different levels, and here we have 16 different data sets scores. And we can see that across different levels of corruption and different types of corruption, FSSD algorithm overall has higher mean and smaller variance of AURC across them. We also conduct the analysis of the ensemble. So intriguingly, we find that FSSDs at different layers are quite diverse, and they can reflect the different features learned in those layers. So for example, ImageNet docs and non-docs both come from the ImageNet dataset. So we suppose that their low-level statistics are quite similar, and their differences mostly lie in the high-level semantics. But for SafeAI and SVHN, they are two completely different data sets. So we expect they are different at all levels of statistics. So finally, here's our outlook for future works. So we've seen some successful cases of using FSSD to detect OOD samples, but we've also actually found some failure cases. One example is that FSSD cannot distinguish between CFR10 and the CFR100 dataset. Such problems clearly requires a deeper understanding of this concentration phenomenon and of neural networks in general. And if we can explain and mitigate these failure cases, we can actually have a clean separation of out-of-distribution data and in-distribution data, just like the MS1M and ImageNet datasets. So here are some future directions that I've been thinking and working on. And either way, they mean just a deeper understanding of how neural networks work on OOD data, which we know really little and really need to know more. And with these understandings, I hope we can build better OOD detection algorithm and safer AI systems. So thank you for listening. We have a code repository here. If you are interested for research or just for use of OOD detection, we've actually implemented a lot of OOD detection algorithms. So I hope it will be useful to you. Thank you.
Thank you, Huawei. Hi, Wen. So we will move the questions for the panel sessions, okay? So we will go to the next speaker. Thank you. So the next speaker is Sashanar. The paper is an evaluation of crash prediction network CPN for autonomous driving scenarios in Carla simulator. Are you?
Oh, 1 second. I'm not seeming to be able to share the screen. I'll just have to leave and join back again. Sorry.
No problem. Yeah, normally you should be able to do it now.
I think it should work now. Can you see my screen now? Hello?
Yes, assume screen. Now your presentation, yeah.
Okay.
Great.
All right. So as I speak to all of you today, I can't help but feel a sense of deja vu, because the last time I was speaking about CPN at SafeAI, I had to present virtually due to visa issues. And now this time again, it seems quite similar. Other than a few things that have changed, that this time we're presenting via Zoom, so you can actually see my face. And that CPN has gone from being just a mere proposition, just an idea in my mind, to being a work in progress and an implementation. Oh, and yeah, I forgot one thing, that in the past year, we've realized the fragility of human existence and the systems that we depend on, which reinforces the idea that we need to think more critically about the safety of all the systems that we've built, especially the AI systems. But I digress. So let's get back to safety in autonomous driving. And we'll look at how crash prediction networks can help us here. Over the next 10 minutes, I'll try to give you the motivation of the project, explain the proposed approach, and tell you how it performs. Despite my personal investment in the project, owing from the fact that I don't have a driving license and I can't drive, there is a real need to think about safety. It turns out that as per a 2018 report on the topic of road safety, about 1.35 million people die due to road accidents in a year. And almost 94% of these are caused due to human error. So the most reasonable approach that comes to mind would be to automate away the humans, which makes sense, but also brings along a new set of problems. which can be seen in the cases of Uber's self-driving car crashing into a person crossing the street, or Tesla's self-driving car detecting the white trailer as clear sky. So this shows that safety is something that we need to think about in autonomous vehicles. And what can we do about this? CPN draws on the idea of safety monitors. And you might ask, what exactly are safety monitors? So you can think of safety monitor as a blanket around the system of interest that tries to filter out all the inputs coming to the system and the outputs from the system. In terms of autonomous systems, there is already something called the Safety Monitoring Framework, or SMOF for short, which identifies the three main states that a system can be in. The first being the safe state, the second being the catastrophic state, which is quite self-explanatory. But the third state, that's the warning state, is the most interesting. Because if the correct intervention is applied at this point, we can push the system back into the safe state. So you might say, there, we're done. We can just slap this SMOF approach onto the vehicle and we're good to go. Well, not really. See, the thing is that SMOF depends on hard-coded values that are decided during the design time. But deep learning doesn't quite work that way. So we need something that is more expressive, that can deal with neural networks. And in comes CPN. So the CPN can be thought of as an ensemble of neural networks, such that each of the networks focuses on different subsystems or subsets of the input, and they all work together to reach a consensus of whether the state action pair is safe or unsafe. For those of you who are more visually inclined, let's look at this. Here we have a ton of neural networks, each focusing on different subsets of the input, and those that focus on the same subset of the input would have different architectures. Each of the networks then produce a classification of safe or unsafe, which then is fed into a consensus machine, here a vote count, to give a final label of whether it is safe or unsafe. So this sounds good, but again, for the scope of the project that we were looking at for this paper, we had to narrow it down to three main points. First is that we only focus on locally avoidable catastrophes. That means those that can be avoided by taking corrective action just when the catastrophe is imminent. And thus, it does not involve any long-term strategic thinking. Second, that we focus only on forward conditions. And thirdly, that even though I said that we'd be looking at different subsets of sensory data, in the following next slides, we'll only focus on the visual sensors, that is the RGB cameras that are mounted on the hood of the vehicle. So now for CPN, we looked at two model variants. One, called the simple CPN, the one that you see on the screen right now, takes in a single frame of input, a single image, along with the action decision from the driving module to give the prediction of whether the state action pair is safe or unsafe. The second, known as the spatiotemporal CPN, or STCPN for short, differs only in the sense that the input now is a short video or a series of frames, along with the action again, to give the same label of safe or unsafe. Just to clarify your doubts, no, the pictures are not there just to make it pretty. The images don't exactly look like that in Carla. The only thing that we've done is, since we did not care about the class of the obstacle, we converted the images to grayscale and then concatenated depth-wise the images from three cameras mounted on the vehicle. And that's the image we get from it with a wider field of view. So now, without getting bogged down into the details, let's just look at the results. Right off the bat, when we compare simple CPN against STCPN, we notice that STCPN performs better and is better able to model the dynamicity in the environment. If you need more convincing, look at the red sections in the confusion matrices here. The main thing that we need to focus on is that the labels, that the data points that are actually unsafe are labeled as unsafe. And clearly, STCPN performs better. So you might wonder, how about when the environment changes, because the environment is constantly evolving? How does STCPN fare there? And as you would expect, STCPN performs really badly. The comparison here is on a small subset of the test set from the previous slide with clear data, and a test set with rainy data. And the one with rainy data, marked by this orange line, does not perform really well. And this brings us back to the importance of using the ensembles that I mentioned earlier. To mimic a setup with ensembles, we've used MC dropouts. And of course, the models here do not, or the results here do not show the exact benefits of ensembles, because the input to all of them is the same. The only difference is in the architecture. But there is still a glimmer of hope, which can be seen by the part marked in red here. If we use an ensemble, we can now determine the uncertainty estimate, which means our models can tell us how sure or unsure they are of their labels and how much trust we should bestow on them. So to conclude, CPN sounds like a promising approach, and has a wide array of things to look into and improvements to work on, and is still a work in progress. But more importantly, for the future versions or the future iterations of CPN, the two main things we should look at is that we always use temporal features, because they can better model the dynamic nature of the environment. And two, that ensembles, beyond helping in averaging out the results, can actually help in also determining the uncertainty of the models. So that's it from my side. I hope you found this helpful, and thank you for your attention. If you'd like to know more details about the paper, or you'd like to get read the more narrative arc about how we went from the simple scenarios with only static obstacles to dynamic obstacles that we spoke about here, please do read the paper. Thank you. See ya.
Thank you, Sasha. So, as always, the questions will be moved to the panel session. So I will go to the last talk for this session.
Can you hear me?
Francisca, or will Maximilian?
It's me, Maximilian.
Okay.
Can you hear me?
Yes, we can hear you. The talk is from black box to white box, examining confidence calibration in different conditions.
Okay, I share the screen. Can you see the screen?
Yes, we can.
Okay, my name is Maximilian Henne. I'm from Fraunhofer IKS. I'm the second author of the paper From Black Box to White Box, examining confidence calibration under different conditions. We did this paper together with the Hochschule Ruhr-West in Bochum. And yeah, now I will start. So first of all, the perception challenge in general is a really complex one, as we have highly dimensional input data like images, where it's impossible to kind of verify each or validate each different combinations of input configurations. They can be really weird and many times out of distribution examples. So formal verification is not possible for this kind of data, that we guarantee some proper functionality for each kind of problem scenario or something like that. So what we need is some kind of uncertainty estimation or confidences which are well calibrated and reliable. For the classification case, this has already been examined, and the goal of the calibration is to decrease or to minimize the expected calibration error. A perfectly calibrated model would be a model where the average confidences match the average accuracy. That means that's for example for all predictions which have 70% confidence, we want these kind of predictions on average to be 70% of the times to be right. There are different methods to achieve this. The most prominent one are something like temperature scaling, beta calibration, or just histogram binning, where you divide the space between 0 and 1 into bins, and then you take the average calibration on each of them. And you can adjust them accordingly with a factor. But before I dive into the calibration part, for object detection, I want to explain some basics about object detectors in general. So we get an input, we feed that into a backbone network, which can be ResNet, VGG, MobileNet, whatever. This is for the feature extraction to get some lower resolution, more meaningful features, which are then later fed into the so-called NAC. This can be some kind of feature pyramid network or other combinations or other layers which combine the different feature maps from the backbone and convert them to even more meaningful features for the prediction. So after that, we have the prediction step. That can be a sort of dense prediction where we have a bunch of predefined anchor or prior boxes, and we make a prediction on each of them. And during training, we do some box matching with the ground truth, and only propagate the loss for these objects which are matching. For the sparse prediction, we have something like a regional proposal network where we get which is trying to predict the regions of interest. This detectors would be like fast RC and N-base, and the dense prediction would be some SSD or YOLO. Now to the calibration part. So instead, for the accuracy or for the classification, we measure the accuracy and try to match that with the average confidences. For the detection part, it's accuracy is not used, as we have a really high number of true negatives due to the a high number of background classes. So we take the precision, so how many of the positives are really relevant, and try to match that with the confidence we get. So for each grid or for each anchor or whatever we have, we can define also this, like in the classification base, we can divide the space into bins and calculate the calibration for each of these bins. So, but we also can take the position, like the X and Y center coordinates, for example, into account. We discovered also a dependency on the position in the image. So, for example, in a previous paper, it was discovered that that boxes at the border in the image, they are less good calibrated than near the center. So, but first of all, I want to give you a small introduction to non-maximum suppression, because this is a really important method which influences the calibration heavily. So non-maximum suppression is if we have many boxes which correspond, or many predictions which correspond to the same box, we just take the box which has the highest confidence out of these. So basically, we suppress all boxes which have a high overlap with the highest confidence box and corresponds to the same class. So that's how we define white box and black box calibration. In white box calibration, like we did in this paper, we take all the predictions. So we don't apply the non-maximum suppression. We take all the boxes we get and try to calibrate them, that the precision matches the confidences. For the black box case, that was done earlier. The non-maximum suppression is applied, and the remaining boxes are calibrated after that. So our results are as this. So we tested on RetinaNet and FastRCN, two really popular object detection models. For the uncalibrated case, for the white box uncalibrated case, we have as we can see on the left, we have a highly underconfident model which was a little bit to our surprise because mostly models are overconfident. But then we discovered that due to the focal loss, and that also matches with other literature, and the focal loss is actually making the predictions less confident. So so on average, it's screwing the curve up, so making the prediction less confident. And after the white box calibration, we have like the calibration error reduces a lot. We get really well calibrated model. The two dashed lines are almost equal. So and for the RCNN, we have a little bit different case. There we have an overconfident model as we don't apply a focal loss function, which is used for the class imbalance problem for the anchor-based object detectors. And yeah, after the calibration, it's much better. But keep in mind that this only applies for in-distribution data. So if we do it out of distribution, the calibration is not that good anymore, but still better than the baseline. One more really important thing is after we take this white box calibrated model, which is like good calibrated, and we apply non-maximum suppression on that, we get a highly overconfident model. That's a problem because we cannot use this in inference time because it's too many boxes. We need a different box merging strategy in order to deal with that problem because the maximum function is basically just making everything overconfident as we take the maximum boxes anyways. So also that can be seen for the position dependent heat map. This is like the dependency of the image coordinates to the calibration, which is like the blue regions are good, the red regions are not. And in the for the calibrated one, it looks much better than for the uncalibrated one. And also for the uncalibrated, or for after the non-maximum suppression is applied, the borders of the image are also less well calibrated, which match previous literature. So to conclude, what we found is focal loss decrease average confidence. White box calibration works as long as it is applied white box also in the inference phase later. Non-maximum suppression is making the predictions more overconfident, and the detection on the border of the image tend to be worse calibrated than near the center. Also, for future work, we suggest that we focus on other box aggregation methods than non-maximum suppression. For example, you can take all your anchor boxes, do some kind of averaging, or some other kind of low computational cost procedures in order to get to really make use of the white box calibration, because the white box calibration itself works really well. Thank you very much.
Thank you, Maximilian. Okay, so we already have the three presentations. I will just... Okay, so we have now debate panel. Cynthia, Chen, who is our co-chair, our chair for the co-workshop, and Rob Ashmore, who will also present later, will be the session discussant. And so I let you the floor, Cynthia and Rob, to ask your questions. But of course, this is open to everyone. If someone wants to interrupt or to ask something, you are welcome.
So I'd like to start. So go, Cynthia, go.
No, Rob, you should go on.
So I'd like to start by thanking all three presenters. I think that was a great way to start off our conference. So one thing that struck me is we're all essentially here looking at things that happen in time. And Sasha, you had a network that actually, used a long short-term memory to look through time. But I wonder if any of us have thought about taking the timepiece out and almost running something separate. So when we're dealing with sequential camera frames, whether this frame's out of distribution, the next frame's out of distribution, kind of taking that as an entirely separate problem. Do we think there's value in that or not?
Yeah, for sure. Like there is some more information if we take like the time dimension and take these kind of changes also into account. At the moment, we are looking into this indeed, but we didn't publish something on that so far. But that's highly important actually. Yeah, the time dimension really matters because, for example, in the object detection case, we often have the problem that some detections which have like 80% confidence, they disappear for the next frame and they get like really low and then they appear again. And so yeah, this kind of, but there are different reasons for that. That can be because of the anchor boxes and their positions, and it's kind of switching from one to another position slightly, but that can make a difference. But there are many reasons for that. So this is really something that needs to be investigated more to depth.
Okay, Sasha, any thoughts?
I haven't really experimented with what exactly you're saying, but I see that having the time component is important because, especially in the case of autonomous vehicles, where you have vehicles that are crossing in front of you, or there are obstacles that suddenly appear, which if you just look at a single frame of data, that does not get modeled. So the time is definitely important, but I'm not sure about having a separate thing, like separate component just for time or not would help. Separate component just for time would help or not. That's something I haven't looked into.
Okay, no, thank you. Huang?
Oh yeah. So like for my method, I don't think it kind of suits for real-time online, like over time frames detection. But like we have experimented something like this before, similar to the like detector. What we find is that it is very so you can like choose 1 in 10 or choose 1 in 5 because it's too expensive. Usually we only choose 1 in 15 or 30. And so how do you choose that frame is very tricky. You can develop some small networks to do it. Like you assign like confidence scores as maximilian set. There will be some frame that the object will disappear. And there are some frames that it will assign very high confidence, so it will be tricky to select the frame. Yeah, that's my current thoughts.
All right, thank you. Cynthia?
Yeah, thank you, Rob. I have a question for Huang. It's just out of my personal curiosity. Do you have any hypotheses or conjectures on why the algorithm can't recognize CFAR 10 and CFAR 100?
I mean, current hypothesis. So
yeah,
my current hypothesis is that there are so what is like FSSD based on to detect different distributions? They are based on the learned features, right? So what we can say is that the learned features from like ResNet model trained on CFAR 10 using standard methods, these learned features cannot, like if we do dimensionality reduction using FSSD, these cannot distinguish CFAR 10 and CFAR 100. So there will be some shared features in CFAR 100, like some spurious features, I think. So like I did some visualizations. The features that are like matter to CFAR 10 is, so CFAR 10 is a very blurry data set, same as CFAR 100. So I think this is the problem because the model is actually not learning very clear features, and these not very clear features are actually shared by CFAR 100. So and they are actually have quite similar distributions. So I think that's the reason why the method cannot distinguish.
I see. Thank you.
I have one more question to Haiwen. As your method is really fast, like you don't need some sampling, like MC dropout or something like that. Do you think that your method is convertible to other problems like object detection?
So I haven't tried that before because I think like object detection problem is kind of a problem itself. It's kind of tricky to do. So what we have, like in previous company, we are a face recognition company, but I'm in the face recognition group, not in the detection group. So I haven't collaborated with them yet. We have tried it on some recognition tasks, like to filter some out of distribution data that are not faces. But I think like I assume this principle works for detection problem, but I know that detection problem is very tricky to do, and like as you may see that even defining a proper metric for this task is kind of challenging. And right, so I think there can be. I mean, we can try, but we'll need some time to see it. Right.
Thank you.
No problem.
Thank you. Is there any other question from Rob of Cynthia or?
Yeah, I have one question for Sasha. I'm interested in how do you generate those unsafe data? You're muted.
Oh, sorry. Now can you hear me?
Yeah.
Okay. So I instantiated a driving module within the Mallah simulator. My first thought was to use an RL agent, which would make sense because you can then have scenarios where it's crashing into things and you collect the unsafe data as those that have crashed into something. But also the other approach that can be used is to add some noise to the actions that are being taken so that it purposely goes and crashes into things. So the label of safe and unsafe is based on whether it is crashing into an obstacle or not crashing into an obstacle. So that's how it is done.
I see. And a follow-up question towards that is, how do you think this CPN algorithm can be incorporated into some other decision-making type of algorithms like reinforcement learning or imitation learning?
So any place where that you expect to have a decision that needs to be made, which is safety critical, you could have potentially an envelope around it, which is a safety monitor. So in this particular case, we looked at autonomous vehicles, but it can easily be extended to any other situation as well. The main idea is that in a sense, it slows down the system so that it can think about its decision and then actually take the action or not take the action. Like that's the intuition behind what is being done. Does that help? Does that answer the question?
Yes, thank you.
Thank you. Is there any other question for the audience? You're welcome. You can just write in the chat zone, or you can just unmute your microphone to talk.
So while everyone's having a think, I'll take another one, which I guess I'll post to paper people, but if anyone in the audience wants to comment on it as well, that would be great. So we've talked a lot about out of distribution data. I'm also hugely interested in what I'd call rare subclasses. So if I have a load of pictures of cats, and let's face it, who doesn't love a picture of a cat? But a very small number of these pictures are actually pictures of white cats. Do we know how our out of distribution detectors, or indeed our estimates of how accurate our model is, how well they work with these rare subclasses. And it kind of gets back to where Beatrice started us off on the day in terms of understanding what the data is telling us. So rare subclasses, any interesting challenges to your methods there?
I mean, like for FSS, feature space singularity, I mean for overall neural networks, this problem is kind of like a algorithmic bias, or say unbalanced data, things like that. And these kind of data problems pose challenges to all kinds of neural networks, in my opinion. So because the data, so it's more like a dataset management problem, because you want your dataset to be balanced. Of course, we can do some algorithms, but for me, I think the main problem is we have to like manage dataset better first, because like for most methods, including like FSS method, what it will behave depends on what you've seen. So if you have seen very little, like very few white cats, like our method will think white cats are not that in distribution, although it will of course be more in distribution than say a dog or some other animals, but it will be less in distribution than the more like black cats, which are seen more often. I mean, that's kind of a universal problem for all kinds of neural network-based methods, I think. Yeah.
So I'd agree with that. I guess one of the challenges is if we want to talk about unbalanced data sets, if I can have the concept of a white cat being a rare subclass, then obviously I can see how balanced my data is with regard to the inclusion of white cats. Yes. If I don't have that as a notion of a subclass, then I guess it's just another case of another place where we kind of know what we ought to be doing, but I'm not sure practically how we can. Because I guess there's an infinite number of different subclasses.
Yeah, I really like the idea of concept, like introducing some attributes or concept, which means more annotation basically. Like for like what we do in MacV is that we have a 100 attribute like project, which means we just add more annotations of attributes to the face image, which like lighting, poster, position. Like each attribute actually have multiple more parameters inside it, and these kind of concepts or attributes can of course really help you to first of all you can make it more explainable, more interpretable, make the decisions or yeah, and of course it can also like help you to do some manipulation, intervention in the test time. Like I've also seen a paper like named under kind of like concept learning by Percy Liang at Stanford. I think they've also done something similar to introduce a concept framework, which can allow you to manipulate or to intervene into during training or test time of the training used by manipulating the concept for like when your data set are not that ideal. I mean.
Thank you. So still not seeing any questions in the chat. Anyone want to unmute and shout out?
Just to answer the previous one, I think also
Please.
that, hello.
Go ahead.
You're good. I can.
Just to answer the previous one, I'd also say that in some sense, and the ensemble system that we're using with CPNs might help as well, because say that the white cat does not get properly detected because it is in RGB data, but it would still have the same shape as any other cat. This shape doesn't really change. So when you have, say, LiDAR data or radar data, you should still be able to detect it. So focusing on different subsets of like multiple subsets as input can help there as well. But but then, of course, if there's something that's completely out of distribution, like if it's never seen a dog, it'll obviously be confused, which is a normal neural network problem. So in that sort of situation, if you have an ensemble, it'll be able to give you an uncertainty estimate, and then you can have a cutoff on how certain you require the networks to be or not to be, which is why I've been pushing towards ensembles for CPN.
No, good point. Well made.
Okay, thanks. Is there any other question for the audience? From Rob, any person?
So since we started with the ensemble piece, so I come from a traditional safety world, and we understand all sorts of things like Byzantine generals problems and 3 out of 4 voters and all those sorts of things. In the neural network sense, where we have trouble, notwithstanding Maximilian's excellent presentation, we still have trouble understanding how accurate any individual prediction is. Are there principled ways of deciding how many types of how many models we want to bring in our ensemble, or principled ways of saying these 2 models are actually sufficiently different that I get some form of independence in my channels? So if ensembles are going to be our savior, how can we deal with them in a principled manner? And that can be to anyone in the audience, I think, because I don't know.
That's the thing that I'm struggling with as well. And that's part of what I'm working on right now. Like, as I said, this current scope was only related to RGB data, but currently I'm also focusing on expanding it to different sensors and trying to figure out how to decide how many networks should be involved and how do you ensure that the networks are independent enough. But I'm open to suggestions. I don't have any ideas there.
So for us, we also did some, like in other works, we also did some experiments with deep ensembles and tried all uncertainty methods, also out of distribution methods. We discovered that like the deep ensembles, like surprisingly a little bit, because it's so simple, perform best on many tasks regarding uncertainty estimation. And we found the number between 6 and 8 ensembles to be enough. So they have almost the same expressive power than if we use 100 or such. Why it works the way it does, or why it's so good, there are attempts to explain it, but it's still not like so clear. Basically, we train the same model with different random initialization, and they kind of always find a different local minima in the high dimensional plane. And this kind of, if, for example, the competing method, the main competing method with deep ensemble used to be like the Monte Carlo dropout, but the variance of the local minima in the Monte Carlo dropout, for example, as we use always the same net, but just we shut different neurons down, is not as high as the variance in the parameter space like deep ensembles. That's what we think why it's working best. But still, back to your question, why, at what point it is enough? That's a really hard question.
So there we go. Good. The answer is 7, and if we haven't fixed it next year, Sasha's going to come back and explain it to us all. So, Chris Harper, question in the chat. Are you happy to unmute and give the question?
Yeah. Sorry, I just thought I'd send you the text in. I mean, just listening to the talk that's going on just now, I guess another question is, which if you've got 100 attributes and you've got to label them correctly, or you've got a lot of distribution, trying to work out what the distribution is, or what is inside or outside distribution. I mean, how the other question is what matters and what doesn't in terms of safety. So and that leads me sort of linking into sort of higher level requirements, because a lot of machine learning life cycles or papers that I've seen presented on that tend to say, well, we assume we're going to be given a set of requirements, and then the problem is to develop the machine learning process from that as a starting point. But I haven't seen huge amounts on the connection between those two levels, and maybe that serves to kind of help guide the sort of determination of or identification of what counts or what the correct distribution should be for a machine learning problem, and therefore what's in and outside distributions. So that's certainly a question that affects, that I kind of think about quite a lot. And maybe thinking more about that might help with some of the earlier questions or discussion points that have been going on.
Yeah,
I don't know if
so as I understand it,
it's an observation, perhaps. But.
Yeah. So thank you. I think so. First of all, the 100 attribute is a project, but it's not actually deployed yet. We are only using it for analyzing, like in real time recognition system. There is just we are just using features. We are not using any the attribute there. But
yeah.
But yeah, I mean, your problem is
that as an example, but
yeah. I mean, right. So I cannot give like further comments on this problem because I'm not expert on the system requirements thing. So maybe other people.
I can maybe think of, like, we can define maybe some kind of requirement that it's detecting all the white cats with a certain accuracy, but it's really hard to say. I think it's only really justifiable if we have some kind of proven by evidence kind of huge data set where we say this is kind of a standard of a data set, some kind of norm data set that we have, like we experience from simulation in the real world, that each model which performs well and detects all the out of distribution examples and assigns good uncertainties on this data set is also translating its performance into the real world. So I think this way, I think that's the way to go, actually, to have this kind of huge information data sets, like, yeah.
Okay. Yeah.
So thank you very much. If there is there are no more questions, maybe we can go to the next session. Is there any additional question? No. So thank you very much, all the speaker, Rob and Cynthia as well, for your participation.
Oh, sorry. I think someone raised a question in the chat box.
Okay, right. One last question. Have someone tried distillation of deep ensemble?
Yeah, interesting question. We do that right now. Yeah. We are currently working on that.
So, Michel, maybe you can contact Fraunhofer people. Okay, great. So